in the transverse direction. And it is just a shorthand way to write this expression over here. Okay? And if you write this in cylindrical coordinate, it will look something like this. If you write this in cylindrical coordinate, it will look something like this. And then it will be something like this. And how do you write a delta function in cylindrical coordinate system? It's kind of tricky, but let's leave it the way it is then, because it's kind of tricky to write it in cylindrical coordinate system. Okay, so if you were to solve this problem, you go through the same method as finding the Green's function of the system. You look for the solution for this system, but this is a solution where you have a line source which is producing a field that is entirely axisymmetric or cylindrical symmetric. So we can assume that there's no phi dependence in this solution. Okay, there's no phi dependence because it's produced by a line source. This must be just a function of rho alone. Okay? And then you can assume that this is 0 for this particular problem. And then you end up having to solve this equation. Delta rho, I don't know if it's correct to say it's delta rho, but it's delta x, delta y. Okay, this is what it means. Okay, there's a singularity at the origin. But this is an equation that is quite well known. Do you know what this equation is? An equation in the cylindrical coordinate system. A Bessel equation, very good. Very good. So the only solution you can have for phi rho are either Hankel function of the first kind with n is equal to 0. This means n is equal to 0. Okay. K rho. Hankel function of the second kind. This is another possibility. Or the Neumann function of the 0th order. Or the Bessel function. These are the choices for your phi of rho. But only one choice should prevail. The others can be thrown out. Okay? The others should be thrown out. Which is one of the four. Why are there four solutions anyhow? It's a Bessel equation. It is a second order ordinary differential equation. Why does it have four different solutions?
The first two are linear combination for the second.
Right, there are only two linearly independent solutions. You pick any two. The other two can be written as a linear combination of the first two that you pick. So there are only two linearly independent solutions. There's one thing you have to remember. The second thing is that of these four possibilities for the above equation, only one is the legitimate one. Which one is the legitimate one? Number 3? This one?
With the second.
The what? This one? This one is a legitimate one? Okay. No? Okay. The first one, the second one, the third one, and the fourth one. All of the above. Right? The second one, you think?
Yeah.
Okay, you think the second one. But unfortunately, I use this time dependence in my course.
Oh, that should be the first one.
The first one, right?
Yeah.
Because only the first one has the behavior of an outgoing one. Okay, if you remember, x is something like 2 over I pi x e to the I x. H02 x is I believe this must be minus I pi x e to the minus I x, or something like that. And then J0x is, this is when x becomes very large. This is maybe pi x cosine of x. I don't know, maybe pi over 4, I don't remember now. There's a constant here, maybe pi over 4. I'm a little bit dubious about that. X goes to infinity, and then y0x. So these are the asymptotic behavior, or asymptotic expansion for x going to infinity. Okay? The first one is an outgoing wave in this time convention. The second one is an incoming wave in this time convention. The third one is a standing wave. The fourth one is also a standing wave. Okay? So the third and the fourth have to be ruled out. The second one has to be ruled out because the physics is wrong. I have a line source, it has to produce an outgoing wave. And then it has to be reminded that only the first, second, and the fourth one have a singularity. Okay? The third one has no singularity when x goes to 0. Okay? J0x tends to 1 when x tends to 0. And then the other one, H01, H02, and Y0x tends to infinity when x tends to 0. So only the first one is regular. I mean, J0 is regular, all the other three are singular. But only one has a correct singularity, which is H01. And then you have to go through this very complicated procedure that maybe Michael Chiao went through with you in finding the Green's function, right? So the legitimate solution is that phi of rho is a constant times H01 K rho. In order to find this constant, you have to go through some work. You try to match that solution to that singularity. You can go back to the first solution. You can write this as divergence of the gradient. You can take gradient divergence and then use Gauss theorem, and then try to pick up a singularity on the right-hand side. And then once you do that, and then you go and look for the small argument approximation of the Hankel function. I believe it goes to like some constant ln of x or something like this. When they go through all this procedure, you find k. Finally, you find that the correct k is I over 4. This is the correct solution to this equation. Okay? I won't go through it, but believe me that that is the correct solution.
Excuse me, from beginning, I wonder why the functions with singularity x equal to 0, that is first handle should be a legal solution.
Yeah, both of all these three, this one and this one and that one, have a singularity at the origin. All of them will go to infinity when x goes to 0. But only the first one is legitimate, because this represents, if I use this for this expression, this would have a behavior of e to the I k rho rho. And when you combine this with this time dependence, this will have something like a function of k rho rho minus omega t. This represents the wave that propagates forward in the rho direction. And hence this is the only legitimate solution. This represents the wave. If you go through this exercise, that represents the wave that looks something like this. The other one would be f k rho rho plus omega t. And that represents the wave that goes in the negative rho direction. Okay? And it's not the legitimate solution. So the first one is the legitimate solution.
The singularity is somehow unphysical, right? Because in the beginning, I think I should not choose something unphysical.
Oh, because I have a line source. The line source has to produce a singular field. the field has to go to infinity at the origin. Okay, so the one with the singularity is a legitimate solution. Okay, let me show you why. Say you have a line source carrying a current, and then if you look at the magnetic field, H phi times 2 pi a or 2 pi rho. Let's assume that I'm performing this integration on a circle just a small distance away from the origin. That integration must be h phi times 2 pi rho must be the total current I that passes through this circle. I'm applying Ampere's law, which means that h phi must be I over 2 pi rho. And rho is very small. Right? H phi is singular. Okay? But H phi satisfies an equation that's slightly different from this one. This one is satisfied by Hx, Hy, and Hz. It's not satisfied by H phi. I think one of the homework I asked you is that why doesn't H phi satisfy this equation? You have to derive a different equation for H phi. But H phi is singular. You can also show that Hx, Hy, and Hz are also singular. You can also show that Ex, Ey, and Ez are singular. Okay, so they have to be singular when there's a line source over there. So the correct solution is the one with the singularity. Okay. And only inside the waveguide. If you're inside the waveguide, the hollow waveguide, there's no source inside. Then these three solutions have to be outlawed because they cannot be the legitimate solution. This is the only legitimate solution when you have a hollow waveguide. And then you pick the third one, the last one, I mean, over there. Okay. So we know how to find this line source solution at least for the homogeneous medium. But this line source solution is not in terms of a plane wave. So we would like to be able to write this expanded in terms of a plane wave. How do I do that? How do we do that? And we do that in this manner. Okay, we do that in this manner. We assume that you have a line source here. The line source produces a field which is described by a Hankel function. Okay. I can use Fourier transform theorem and take a cross section at a place where y is a constant. And then I can say that phi x of y must be equal to a Fourier transform of the kx e to the I kxx phi tilde kx y. This is just a Fourier transform statement. Okay, this is just a Fourier transform statement. And why is that I can do this? What is the reason that I can write a function of x in terms of a Fourier transform? The reason is because this function is a complete function. Mathematically, it's complete. Okay, it's complete. And also orthogonal. Okay, so if you don't know this notion, you can be in trouble. You can be in trouble. Okay, the notion of completeness. Because someone just wrote a paper in AP transaction, ignoring this fact and wrote down a bogus solution and published it in the IEEE transaction because he didn't know the concept of completeness. Okay, so this is complete. Because this is complete, you can expand any functions of x in terms of that. Okay, and if that is the case, if I plug this into the equation, if I substitute this into this equation, then I change the order of integration and differentiation. I take this inside, okay, the integrand, and this partial squared partial x squared operating on this will give me minus kx squared. Okay, this one I can write it as partial squared partial y squared. And then I can have k rho squared. P tilde kx y. So can you see how I could go from here to here? I just exchange the order of differentiation and integral. Take the differentiation, the differential operator, and let it operate on the integrand, and when it operates on this, partial squared partial x squared just becomes minus kx squared. Okay, that's one thing I did. And then on the right hand side, I'm going to make use of the fact that delta x is 1 over 2 pi minus infinity to infinity dkx e to the I kxx, right? All of us somehow know this from my electrical engineering courses. The delta function can be written as this, because this thing is complete. But if you give amplitude of 1 everywhere, this is actually not a convergent integral, but is accepted by most engineers and mathematicians and physicists that this is correct. Okay, so now I can write the right hand side as 1 over 2 pi and then because of that I still have a delta y term left. Okay, so if I have this now and I have two things equal to each other, with two Fourier transforms equal to each other, when can I say that the integrands are equal to each other? We have two integrals, and these two integrals are equal to each other. When can I say that the integrands are equal to each other? I cannot just simply equate the integrands. If you do that, the answer might be wrong. Right?
The basis is the formula?
The basis of the formula and complete. This is very important. Okay. When this basis, this is our basis. Okay, if you want to use the concept of basis. If this basis functions are complete and orthogonal, then the integrands are equal to each other. Okay, this is a very important mathematical concept. And to do it more thoroughly, you can multiply this equation by, if you want to do it mathematically and thoroughly, you can multiply this equation by e to the I k x prime x and integrate over all x. Okay? And when you multiply and integrate over all of x, then you will pick up a delta function with this term. And then you will also pick up a delta function with this term. And then the dkx integral will go away. And then you can equate the two integrands. So the basis is orthogonally complete because we know that this is true. Something like this. Okay, this is also true. This is true because this is orthogonally complete. Okay? And then because of this fact, we can equate. You can equate the two integrands now and say that the equation I have is b squared dy squared plus k rho squared minus kx squared phi tilde kx y is minus, there should be a minus sign there, there's a result, delta y. Okay? And you can call this ky squared. We call this ky squared. And this equation is often encountered in electrical engineering. And you know the solution to this equation, right? It's when you solve problems with impulse response, with the time domain, you need this equation, but you don't need to impose causality in this equation. You can just have a two-sided function, a non-causal solution. You want me to derive for you? I can just write it down, right? You will just forgive me if I just write it down. You tell the is equal to I over 2ky equal to iky. Why? You want me to prove this, or you can take it as it is? You want me to prove it? Okay, maybe I take a break and then prove it after the coffee break. To prove that this is in fact the solution to this equation. Okay? Let's take a coffee break and then I can prove that. Or at the same time you can muse about it and think about how to prove it when you're on coffee break.